Okay, welcome back. So we've been talking about heat capacity, and now we are going to think about how the heat capacity for ideal gases and real gases actually shows up. And with this, we're going to start making some connections to the statistical mechanics that we've spent the last 5 weeks working on. Okay, so statistical mechanics, we started with the partition function. We started with Boltzmann's distribution. And it turns out that statistical mechanics is able to make all of our explanations. Now, because we went through the effort of moving from the Boltzmann distributions and the partition functions into the equipartition theorem, we're going to rely heavily upon the equipartition just because the math is so much easier. So if we start with equipartition, the energy of the system is defined by these terms. We covered this. And we know that CV is equal to the partial of the energy with respect to temperature. So that means that CV is going to be equal to 1/2 NEP times NR. How did I get there? Well, I took the derivative of the energy with respect to temperature at constant volume, and I'm going to take the derivative with respect to temperature at constant volume of 1/2 NEP in RT. And I know that the derivative with respect to T is just going to be this 1/2 NEP in R term. And so I get that and I know that this term is equal to CV. And so I get 1/2 NEP in R. Okay, so let's do an example. I want to determine the value of CV for 2 moles of neon gas. And so we know that CV is equal to 1/2 NEP in R. And we have neon gas, and so NEP is going to be equal to 3 because we only have translations and we have we're going to assume a 3-dimensional world. Not always the case, but for the most part. So CV is going to be equal to 1/2 times 3 times our 2 moles times R, 8.314 joules per mole Kelvin. And I get that CV is going to be equal to 24.9 joules per Kelvin. Okay, so the challenging part of this one is what we've been working on, which is counting the degrees of freedom for molecules and atoms. Okay, now for CP, we can go through a very similar derivation. It's a bit longer because it's CP and everything's more complicated. But we're not going to do that. We're going to, if you're interested, see page 253, 254 in your textbook. And once we do that, we find that CP is equal to 1/2 times NEP in R plus NR. So let's do an example. Let's determine the value of CP for 2 moles of neon gas as predicted by the equipartition theorem. So for neon gas, NEP is going to be equal to 3. And so CP is going to be equal to 1/2 times 3 times 2.00 moles times 8.314 joules per Kelvin mole plus 2.00 moles times 8.314 joules per Kelvin mole. And so Cp is equal to 41.6 joules per Kelvin. So again, the tricky part here is counting our NEP and making sure that we understand what the degrees of freedom that are going on happen to be. Okay, so you're probably going, wait, hold on. How is it that it doesn't matter what molecule, what atom I put in, I get the same heat capacity? Well, it turns out that CV is related to temperature, but it's really related to temperature based upon the equipartition theorem. That at very low temperatures, we only have translational motion. And so there's, at very, very low temperatures, there's really just this 3/2 sort of energy. Adding a little bit of temperature starts to populate rotational levels. And then for a linear molecule, we get 2 more degrees of freedom and can get up to 5/2. And then once we raise the temperature enough, but notice that it really starts at like 1,000 Kelvin. Once we start raising that temperature enough, we start getting the vibrational levels populated, and then we can get a lot more energy. And so, yes, our systems really are defined this simply. That the energy that we're putting in, the heat that we put in, has to go to something. And that something is translations, rotations, and vibrations. And the equipartition theorem really helps us define how that temperature is going into our different types of energy. So, how good is this? It turns out that if we have gas phase atoms, like helium, argon, neon, these tend to be very close to the equipartition value. The more atoms that there are in the molecule, the more equipartition heat capacity overestimates the experimental heat capacity. As the mass of the molecules increase, vibrations become much more significant contributors of the equipartition. And really, the lower limit of the heat capacity is estimated by the equipartition, including rotations and translations, but not vibrations. Okay, so let's talk about this a little bit. Let's talk about this one especially. So the more atoms that there are in the molecule, the more that equipartition overestimates. Well, it turns out that this is really a result of adding some vibrational degrees of freedom. Remember how in one of the first homeworks we talked about the temperature and these really low energy torsional motions that happen in proteins? Well, it turns out that you don't have to have a protein to be able to have torsional motion. And once you get something large enough to get some of these low energy sorts of vibrations, then the equipartition starts falling apart. And it also turns out that equipartition assumes that every type of energy is, every degree of freedom is absorbing the same amount of energy. And it turns out this isn't exactly true because vibrations are so variable and they really scale quickly with the size of the molecule. And so the more atoms, the more vibrational challenge you have to making approximations using equipartition. Then as the mass increases, vibrations become more significant. And so it turns out that our equipartition actually gets a little bit better with heavier atoms. And this is because that when we have really large atoms attached to our bonds, our vibrational frequencies are very low. And so a little bit of temperature starts contributing into those vibrational motions a lot sooner, and our equipartition works a lot better. Okay, so because I know you're not going to believe me, I'm going to show you some data. So when we say equipartition, this means that this is the calculation of NEP with rotations and translations. And then when we say full equipartition, this is going to be NEP with rotations, vibrations, and translations. And these numbers in between, these are experimental. And so you can see how when we have a hydrogen atom or a nitrogen atom, our experiment and our equipartition, actually full and simplified, because remember these are atoms, so those are the same, these are really good. Bromine and iodine are really good too. Fluorine and chlorine are a little bit off, and this turns out that there's some strange electronic transitions that can happen here. And we haven't talked about how electronic factors into equipartition because it usually doesn't. But in these cases, it does. And that's how we explain those differences. But even once we start into diatomics and we start looking at our upper limit of our full equipartition and our lower limit of our simplified equipartition, that our experimental values fall in this range. And really, we're not off by that many joules. Even once we start getting, and so as we start getting things bigger, we start noticing how there's a lot more variety. And we start seeing things where heavier atoms look more like full equipartition. Lighter atoms look more like the simplified equipartition. Okay, so bottom line here is that we can approximate these things with the equipartition theorem. It does work, but it is an approximation.